This is the Convergent Science Network podcast. Leading researchers in the domain of neuroscience, brain theory, and technology are interviewed by Paul Verschure and Tony Prescott.
Okay, this is Tony Prescott for the BCBT 2011 Summer School, and I'm talking to Federico Carpi from University of Pisa Research Centre Enrico Piaggio.
Hello.
So Federico, this morning you gave us a really interesting talk about the next generation, or what might be the next generation of actuators for robots and many other applications. So before you tell me what these new actuators are like, can you explain why do we need new actuators? What's wrong with the tiny little motors that we've got already?
Yeah, there are a lot of, let's say, problems that must be overcome with traditional actuation technologies. One of them certainly deals with the fact that they use stiff material, mostly metal. And so this means that they are using some constitutive material that are actually very, very far from the natural tissue that our bodies are made of. So we are talking about some stiff components as compared to soft tissue that makes our bodies. And this is particularly important because, and this aspect I would say has been completely neglected so far. Attention has been made only on the psychological aspect on one end and the neurophysiological aspect of replacing human-like machines. But the body itself is really important. And another aspect, for instance, concerned more technical issue like acoustic noise that traditional motors generate, which is not something really pleasant for user, especially when we consider technologies or systems that have to work in close contact with humans. For instance, rehabilitation system like orthotics or prosthetics. And there are also other issues, for instance, power consumption, energy consumption. Basically, electric motors are really demanding in terms of energy consumption, which make this aspect challenging for if we consider portable application, for instance, so in terms of autonomy of the robot. So these and other issues suggest that we should look for some alternative technologies based on materials that are inherently capable of exhibiting a sort of any kind of response, useful response to a suitable electrical stimulus. In particular, we are looking for materials that are able to deform or change shape according to an electrical stimulus. So we are looking for so-called electromechanically active materials.
So these would be in some way more similar to a sort of animal actuators or muscles.
Exactly.
I mean, what are the nice properties of animal muscles that you think we want to try and copy?
For sure, we are looking for materials that should be able to exhibit both strain and stress, active strain and active stress capabilities, as I said, in response to an electrical stimulation. And for sure, we are also looking for a combination of actuation and sensing. These two features should be integrated in the same material. So in this respect, these smart materials should be able to self-sense their own state, mechanical state, in terms of, for instance, of deformation. So we are opening here a different paradigm with respect to the state of the art. Nowadays, we use actuators and sensors typically as different components in a robot, and the two components are, of course, interplay and, of course, are part of the same system, but in any case, they are different devices working with different principles of operation, and frequently they are also arranged in different position, a different location of the robots. On the other hand, in the human being, or in general in the animals, the device, let's call it like this. The device itself is both an actuator and a sensor. Our muscle inherently have the sensing capabilities. So it's the material, it's the tissue itself that work both as an actuator and as a sensor.
So our muscles are made up of cells, and each of those is itself very complicated.
Oh yeah.
So how can we use materials to build something with?
Well, the idea, of course, is not to replicate the cellular structure of the natural tissue, but the idea is to replicate the functional properties. So in terms of actuation and sensing. From this respect, the so-called electromechanically active polymers seems to be really, really interesting. And there's a lot of competence in Europe on that.
So for somebody who's not a chemist, what's an electrically active polymer?
Yeah. So they are just a piece of matter. A polymer can be of different types of synthetic form. One of the most useful nowadays consists of so-called dielectric elastomers. Strictly speaking, just a piece of insulating rubber, nothing more, like a piece of silicone, which is an electrical insulator, which can be deformed as soon as it is charged properly from an electrical point of view. And we can enter, if you wish, the physical principle. I will try to explain it in simple words.
I think if you could explain very briefly how passing current through a piece of rubber can make it.
Well, actually, it is not really a matter of passing current, because the principle is just an electrostatic effect. So in simple words, you have a layer of an insulating elastomer, as I said, a piece of silicone, for instance, and you cover this layer on the main surfaces with two electrodes. And these electrodes should be compliant, so deformable. And in this way, you have a capacitor, what the engineer called a capacitor, an electrical capacitor. As soon as you charge this capacitor electrically, the charges on the electrodes basically interact according to a simple electrostatic effect, so Coulombian forces. So basically the plus and the minus attract each other, and the charges of the same sign repel on the electrodes. This effect combined together squeeze the insulating layer between the two electrodes. So we have, practically speaking, really a compression of the material. And since these elastomers have a constant volume, the compression along the thickness is parallel to a surface expansion, because the volume should be constant. In this way, we achieve a significant actuation, so a significant deformation of this capacitor as soon as it is charged. So the principle of operation is extremely simple, a purely electrostatic effect, which is known as Maxwell stress effect. It is not a piezoelectric effect. I want to remark it is different.
So the principle is that we're using this electric field to squeeze a piece of rubber.
Exactly.
Okay, and then how can we use that as an actuator to move things?
Yeah, so this is the physical principle. Then we can build an actuator by opportunely designing the shape, what we call the configuration of the device. For instance, a simple piece of rubber with planar shape is a very elementary actuator, but it is useful for many tasks. Then if we stack in a sort of pile multiple layers, one on the top of each other or the other, we achieve actually a pile, a stack, and this is very useful, for instance, to have larger deformations, because each layer will contract and the whole pile, the whole stack, of course, will contract accordingly, but you achieve a higher absolute contraction, of course, because you have a taller, a bigger pile. That's it. This is what we call stacked actuators, for instance, but there is really plenty of different configuration available nowadays. Many groups have demonstrated a lot of them, including our group in Pisa. And for instance, these include a linear actuator or membrane-like actuator, bubble-like actuator, really any kind of configuration. The limitations are mostly in our imagination, I would say. This technology, this is really interesting. An interesting point, this technology is highly versatile,
right,
scalable, and is really suited to be shaped according to the need of the specific application.
So I can see how you can get this thing to deform and therefore actuate.
Yes.
But how can it be intrinsically sensing?
Yeah. You can use their sensing capabilities in two respects. One is the so-called piezo-capacitive effect. So basically, as we said, the device is a deformable capacitor. So if you read the capacitance, the electrical capacitance of the device while it is undergoing the deformation, you have a signal which is correlated to the deformation itself. So by reading the variation of the capacitance, you have an information on the deformation state of your device continuously. So the actuator is both an actuator but also a piezo-capacitive sensor. You could also exploit another concept, another principle, which is the piezo-resistive effect. So in this case, if you need to read a resistance, a variable resistance, like any conventional strain gauge that it is used everywhere in industrial products. In this case, as I said, you have to read a resistance, which can be either the resistance of one of the two electrodes or of the resistance of an additional layer, conductive layer, that you integrate in your device. It is very easy to achieve a sensing signal. And this is extremely stimulating because, as I said, in this way we achieve an integrated sensor and actuator all in one. And this is, from a functional point of view, very similar to what is available in our natural tissue.
So we can build these quite compact devices that can actuate and sense.
Definitely.
So what's the drawback? Because why aren't we putting them into all our machines now? There's still some problems to solve.
Sure. As usual, there are advantages and disadvantages. For instance, you said properly that you can achieve very compact structure. That's why the first product, which has been launched this year with a huge expected commercial impact, is a product for consumer electronics. Maybe I cannot say here the specific company because, can I say my
I think you can. Yeah. We can edit it out.
Yes. But by the way, it is a big company which sells consumer electronics like cell phone. And in this case, this company has replaced the electrical motors that are used to provide vibration to the mobile unit with these material, electromechanically active polymers, in particular dielectric elastomer actuators. And they have produced these actuators as thin films, very thin. So this is very appealing in order to integrate them in a thin portable device like a cell phone. And these devices are very thin, very compact, they are very lightweight, and they consume very low power because they are capacitor, electrical capacitor, so they do not need to be driven with high current. That's a great advantage in order to save energy, so in order to enable a really portable application with low power consumption.
So to get a vibration out of this sheet,
yes,
what are you doing to the current in order to generate the vibration?
Oh yes, you have a sinusoidal voltage, for instance. So you charge and discharge your device.
So it's very straightforward from the current that you supply to the behavior that you get.
Sure. There's a specific relation which is not linear, but it is specific. It is a quadratic response. I mean the stress that you can generate in this material is proportional to the square of the electric field.
So the electric pulses that we use when we move our muscles, can we use those similar kinds of pulses to drive these sorts of materials?
Yes, we can, but it really depends on the application if it is useful or not.
So
for instance, we have
a medical application, for instance.
Yeah, for instance, we have demonstrated, but it is a very simple experiment that you can drive this material with electromyography. That's very easy, like any other actuator. So that's not a critical point today.
So this would be where you would record signals directly off of somebody's muscles.
Right. You record signal from your muscle, from the patient. And let's imagine, for instance, the need for a prosthesis, which is equipped. We should be equipped with actuators in order to be an active prosthesis, and you have to control the device, possibly using the physiological signal captured from the patient himself. So in this case, you capture muscular activity from any part of the body. For instance, if we are talking about a prosthetic hand, maybe from the forearm, and you capture this electrophysiological signal, and with a very simple elaboration in real time, you can drive your actuator in order to perform a specific task. This is feasible also with other actuation technologies. I don't see any difference with other technologies from this respect. In any case, we have confirmed that even using electroactive polymer, this can be done. And this is important, of course.
But you think there's some particular areas where this technology might be much better?
Definitely. There are at least 4 emerging areas where this technology shows a great potential over any other actuation technologies available today. The first area is mechatronics, and in particular variable stiffness devices. For instance, in the biomedical field, we are talking about variable stiffness system for rehabilitation. We are developing a so-called hand splint orthosis in order to perform customized rehabilitation of the hand for post-stroke patients. So this is a big field of interest.
So an orthosis is a support for the hand while it's healing?
Right. It is a support. And in this case, the hand orthoses are called hand splint. Basically, they are used to, they are dynamic devices in the sense that they are equipped with elastic bands or springs in order to allow the patient to voluntarily move his fingers against definite loads, counter loads provided by the springs or the elastic bands in order to perform an exercise of their fingers. For instance, for this application, we are developing an active version of this passive system of the state of the art by replacing the springs or the elastic band with these elastic actuators. So the future splint will not be equipped anymore with passive springs or passive band, but will have active bands. Active in the sense that by using an electrical control, you can modulate the stiffness of your band. So you can modulate the compliance, and so the patient can really perform a customized training against controllable loads. So the load is no more predefined a priori, but can be adapted in progress to the specific need of the patient. And this is important.
So can you explain a bit how you can vary the stiffness? So I can see that
yes,
when you take this polymer and you apply the current, you can change the shape. But how do you change the stiffness?
It depends on how you basically, the specific constraint how you use your material and your device in general. It is a little bit technical, this part. Maybe it is difficult. But
the question would be, can you choose any level of force and at any level of stiffness, or is there some relationship between those two?
We have demonstrated, but this had been anticipated also by theoretical calculation. We have demonstrated experimentally that you can really control the stiffness. So no more a simple position or force control, but a real stiffness control. You can really control the stiffness, which is basically the slope of the force versus the displacement. At least what we call the static stiffness. And this can be done, we have demonstrated. So it is important for as I said, for instance, for biomedical application oriented to rehabilitation.
So if you can control the stiffness, then there are lots of applications in virtual reality where you might be able to to use this as a display.
You're right. Yeah. You're right. But maybe not always. For instance, imagine about vibration damping in vehicles. There are many activities going on, especially in Germany, where there are a lot of car manufacturers interested in using this technology for vibration damping in cars, for instance. So if you can control the stiffness, let's say of some in parts of the interior of the car, or someone is even thinking about something more challenging, maybe the motor itself, and you can really damp vibration. This can be useful for the vehicle, but also for the passengers in order to make the travel smoother. By the way, this is work in progress.
Yeah. And can you give me an example of where you might use this material to display something that I might feel on the skin, which would, and to represent or to change the property of that surface that I experience through touch, through haptic?
Yeah, so you're talking about haptic devices. Yeah. Yes. That's another interesting area where there is significant potential. For instance, we are developing a braille display. So a tactile display for the blind people. The state of the art of this display is the following. Basically, you have some dots, plastic dots, which go up and down and form the braille character. So the braille code for the blind people. And the unit braille cell consists of 8 dots. By changing the status of these 8 dots, different combinations provide different characters. So in these devices, the state-of-the-art devices are driven by cantilever-like piezoelectric actuators, which are very long. Let's say a long, rigid shaft, which push these dots up and down. And the problem is that the encumbrance of these devices is very high. They are very bulky. So you cannot today implement more than two reading rows because of the volume constraint. That's it. So Braille displays as a full page representation of the Braille code are not achievable today with the state-of-the-art technology. So in order to overcome this limitation, let's say try to develop a sort of electronic book for the blind people, as we have in the tablet nowadays, you really need a technology really more compact. And for instance, we are developing now with the help of a company, we are developing some small dots, Braille dots, and each dot itself is both the actuator and the Braille dot. So we have tiny bubbles that goes up and down, and we hope that we will be able to demonstrate a new Braille display soon.
And you could imagine, as a generalization of that you could take surfaces and you could change in real time their haptic properties.
Texture,
so you could, you could take something that's smooth and it could become ribbed.
Yes.
And there could be all sorts of interesting applications for that.
A group, the fathers of this technology in the US from the Stanford Research Institute some years ago have already demonstrated some prototype with texture changes, changing surfaces using this concept. Well, not exactly this concept, but something close. But by the way, using this technology.
So in the future, you might imagine something that was like a sheet, which would deform itself to form a tactile picture of an object.
That is a dream, but it is realistically achievable from our point of view. It is a matter of trying to miniaturize and, the technology, improve the resolution, but it is technically feasible. I would like to add a comment about other possible areas. We said mechatronics, Another big area is energy harvesting, because
So this would be where you drive it in reverse?
exactly in reverse. You can generate electricity by harvesting mechanical energy from the exterior. So if you deform this material when they are electrically charged, and then you release the force that you have applied to the material to deform them, then the electrical charge stored in the material increases the electrical energy. This can be easily demonstrated with calculation, but also with experimental test. So basically, you convert the input mechanical energy into output electrical energy. And for instance, there are a lot of studies nowadays and also experimental tests to harvest the mechanical energy from the ocean waves.
So this is it's not too different from an existing electric dynamo, presumably.
Exactly.
So,
somehow the concept is the same,
Yeah.
but the principle of operation is different.
Mhm.
Yeah. And this is very useful nowadays because, we all know that worldwide energy consumption is increasing. We need renewable energy sources. And for instance, if we imagine the sea waves are an enormous provider of free energy, it is just a matter of finding the best technologies able to harvest this mechanical energy. Similarly, we can harvest energy from the wind using the same technology.
Is the idea that this would be more energy efficient, and that's largely
I would say for sure that will be much more cost effective because you can produce very large surfaces at low cost, and this is not feasible with any other technology because this technology is polymer based, and polymer are very cost effective material. So this is a great advantage. Moreover, they work nicely at low frequencies, especially at low frequencies. So they are nicely complementary to conventional technologies based, for instance, on piezoelectric energy harvester, which nicely work at resonance at higher frequencies. So this is another interesting field.
So that another thing that you were mentioning is that you're taking biological inspiration from another place, which is from how humans use their eyes.
So, exactly. Optics, tunable optics is the last really emerging field of application. And we are quite happy because we have recently demonstrated the first tunable lens inspired to the architecture of the crystalline lens in our human eye. So basically in our eye, we have a lens which is deformed by the action of some muscles, which are called ciliary muscle, which basically stretch and release the crystalline lens in order to shape its curvature, and then in order to change the focus.
So the lens is a bit like a soft ball that you can pull it one direction, make it flatter, and squash it and make it more spherical.
Exactly. And we have some dedicated muscle for this action in our human eye. Similarly, we have produced two membranes filled with a fluid surrounded by one of these dielectric elastomer actuators. Everything has been developed in our lab. And the actuator, as a real artificial muscle, is able to deform the lens radially, so to change the focus. And we have demonstrated, as you have seen this school also live. I have brought a demo. You have seen how nicely it is able to really change the focus. So we expect that this biomimetic approach will really provide some new capabilities to tunable lenses in order to make them really compact, lightweight, again, power efficient, and very cheap at the same time.
And could you imagine a future prosthetic eye which was using this technology?
That's our dream, actually. We are working for a prosthetic eye based on this technology.
So all these prosthetics sound amazing, but one thing that I've heard about these EAPs is that you have to put an enormous voltage across the surface, and that sounds quite terrifying.
Yes, it is terrifying, but if you don't know the full story, let me make a remark on that. It is true that you need high voltages, today in the order of 1 kilovolt, because we have materials that are completely not optimized for this purpose. Nowadays, we use some, for instance, silicones, which have been developed by industry for other purposes. So these materials do not have specific electrical properties tailored for this application. In particular, they do not have high dielectric constant. And the higher is the dielectric constant, the lower is the electric field that you have to apply. And so the lower is the voltage that you have to apply. So this is a problem related to material science that is now faced by several groups, because it is really evident that if we want to reduce the driving voltage, we have to increase the dielectric constant. On the technological side, however, we can still play with available off-the-shelf material by simply manufacturing thin layers. The thinner is the layer, the lower is the voltage that you have to apply, because the important parameter, the important variable, is the electric field, which is the ratio between the applied voltage and the thickness of the layer. So lower thickness, lower voltages. And in principle, but also in practice, you can drive these materials with voltages of the order of 100 volts. This has been already demonstrated by many groups. So this is not a major issue for the future.
But will it require special ways of manufacturing to make these things?
Yes, using voltages of the order of 100 volt, which is the same order of magnitude of piezoelectrics, is not so dramatically difficult. It can be done even by university lab, not only by companies. The problem is that if you want to drive them at 10 volts, that is really challenging, because you need an order of 1 micron thick film, which is challenging with this material because they are extremely soft. So in the long future, certainly this is the direction to be faced, but we still have to see, the real possibilities from that point of view. But I have to remark that it is true that this can be a challenge, but not a critical point from a technical standpoint, because you can easily produce these high voltages with very compact multipliers. I mean, very compact, I say a few cube millimeters. So very, very simple electronic components can generate these high voltages because you don't need high current. And this is the key point. You need to drive this technology with high voltages, but you don't need to supply high current, because these loads are capacitive loads. So they do not absorb high current like a resistive load. And this is a winning point.
So even if you get a shock off this, it won't kill you.
Yeah. Even if you get a shock, it is unpleasant, like a shock that you get from your car, but it is not dangerous. That's very important. And that's why, for instance, I mentioned before, a big company has been able to deliver on the market the first portable application for a mobile phone. This has been possible because the current that you have to supply is small, so you can simply use a battery like the battery used in our cell phone today. It is not dangerous, so it is allowed for commercial product to play at 1 kilovolt with no risk. So it is true that maybe for the man of the street, this can be a scaring factor, but actually it is not a technical problem nowadays.
So we'll be carrying around these things in our pockets that have 1 kilovolts,
yes.
And they won't be able to do
if you go to the market tomorrow, you still can buy, you already can buy one of those mobile phones. So you will have 1 kilovolt in your pocket.
So in 10 years' time, what do you predict? What's one of your predictions as to a device that I will be using perhaps every day?
I predict there will be really an explosion of this technology, because I've seen that from the last 10 years. 10 years ago, the first paper on science, on the fundamentality of this technology was published, really 10 years ago. In 10 years, we have achieved the first industrial product in a mobile phone. And 10 years for a new technology are really nothing. So it means that the technology is really promising, is really suitable for great developments, and I expect that the next 10 years will provide a great evidence of the importance of this technology.
And if there was a specific technology that you could mention that you'd be really excited about having in 10 years' time, what would that be that would use this?
I mean, the specific product?
Yeah.
Well, for sure, optical devices and haptic devices will be the major fields of application. So, for instance, tunable lenses and vibrotactile devices will have a great role.
So when you say a vibrotactile devices, you're thinking of something like the Nintendo Wii controller, which now buzzes in your hand when you're playing a game.
For instance, this is the current application.
So in 10 years' time, what will that be doing, that vibrotactile device?
Well, as a biomedical engineer, I have a dream. I hope that in 10 years, at least some of our efforts will have been useful for the blind people. This is my greatest wish, because we will really enable something which is not possible today. So a great advantage for the blind people. Yeah.
Okay. Well, thanks very much for talking to us. It's really interesting.
Thanks.
The CSN podcast was produced by the Convergent Science Network of Biomimetics and Biohybrid Systems, a project funded by the European 7th Research Framework Programme. For more interviews, recorded lectures, or upcoming conferences in the field of biomimetics and biohybrid systems, go to csnnetwork.eu. And thank you for listening.